Have you ever looked up at the stars and felt a sense of wonder about what lies beyond our world? Get ready to embark on an incredible journey through the vastness of space, where reality is more awe-inspiring than any fiction. Today, we're diving deep into the mysteries of black holes, where the laws of physics take on a whole new meaning. Join us as we unravel the secrets of these cosmic giants and explore the very fabric of the universe itself. From the groundbreaking discoveries of Newton to the mind-bending theories of Einstein, we'll trace the evolution of our understanding of gravity and venture into the heart of these enigmatic phenomena. But hold on tight, because we're about to challenge everything you thought you knew about the cosmos. Recent research suggests that the infamous singularity at the core of black holes might not be as inevitable as we once believed. Could this be the breakthrough we've been waiting for? Get ready to expand your mind as we journey through the twists and turns of space-time, confronting the most perplexing questions in modern physics. And don't forget to share your thoughts with us in the comments below. We want to hear your take on the wonders of the universe. So, fellow space enthusiasts, are you prepared to push the boundaries of human understanding and embark on an unforgettable voyage through the cosmos? Then hit that subscribe button and join us as we explore the universe together. Let's boldly go where no one has gone before. Many, perhaps most physicists were seriously uncomfortable with the idea of black hole singularities, and they got even more uncomfortable when, in 1965, British physicist Sir Roger Penrose showed that singularities really are unavoidable in general relativity. His Penrose Singularity Theorem, for which he won the 2020 Nobel Prize, claims that as long as an event horizon exists, so must a singularity. Perhaps the most important implication of the Singularity Theorem is to show that general relativity really is in fundamental conflict with quantum mechanics. If that's the case, then the only salvation from the paradox of the singularity is some greater theory combining quantum mechanics and general relativity, in which the singularity will evaporate away as if it was just the bad dream of ignorant 20th century physics. But just recently, we've had a ray of hope from a completely unexpected direction. In a paper released in December, Roy Cur, one of the greatest black hole theorists of all time, may have shown that we can avoid the black hole singularity without quantum mechanics after all. In order to get to this radical new result, we need to build up some understanding. So let's refresh our knowledge of black holes and review the Penrose Singularity Theorem. Then, maybe we can decide if Roy Cur really did destroy the singularity. So to start with, Roger Penrose didn't exactly prove the existence of singularities, not explicitly anyway. He demonstrated that space-time paths must terminate inside a black hole. Anything moving in space-time under only gravity follows something called a geodesic. This is a path through space-time that minimizes the combined spatial and temporal distance traveled. Before the Penrose Singularity Theorem, it was generally held that geodesics had no end. An object might travel along a segment of a geodesic, for example, a ball being thrown on a parabola, but the geodesic itself can be traced both backwards and forwards beyond the ball's trajectory. Forward forever into the expanding universe, or backwards to the beginning of the universe. Roger Penrose showed that inside a black hole, geodesics have to converge at the center and end there. When a spacetime admits geodesics which don't go on forever, we say the spacetime is geodesically incomplete. You can imagine geodesics as the grid lines of spacetime, forming a smooth, if sometimes quite warped fabric on which the laws of physics work nicely. Geodesic incompleteness means there are pinched-off regions where infinities appear and the laws of physics break down. So the argument of Penrose was that geodesic incompleteness means singularity. But Cur has an objection to the argument, and it depends on a subtle interpretation of geodesic incompleteness. So let's dig a little deeper. When Penrose said a geodesic captured by a black hole ends at the black hole center, he meant something very specific, mathematically. He meant that the geodesic parameter is bounded, so the mathematical variable we use to describe the evolution of something along a geodesic terminates. Similar to how your latitude terminates if you travel to the South Pole, you can't go further south once your southness is maxed out. For the geodesics describing the paths of matter, the geodesic parameter can be, and usually is, taken to be the proper time. That's just the time measured by someone moving along that trajectory. So if the parameter for a matter geodesics is bounded, that would imply a singularity because there's no way to trace a flow of time through it. There's no meaningful way to define after the singularity in either space or time. These are dead ends in space-time. But Roy Cur had his doubts, to put it mildly. Cur is a New Zealand physicist who, in 1963, came up with the Cur Metric, the mathematical description of a rotating black hole. This was the second black hole solution to the Einstein equations to be discovered 47 years after Karl Schwarzschild's solution, and that one just describes the much simpler case of a non-rotating black hole. Now we have good reason to believe that essentially all real black holes have some rotation, so the Cur solution is kind of a big deal, as is Roy Cur, and Roy Cur vehemently disagrees that singularities exist, nor even that the Penrose singularity theorem has anything to say about their existence. Let's finally get to the heart of his objection. As we wrap up our cosmic odyssey, let's take a moment to ponder the profound discoveries we've unearthed together. From unraveling the mysteries of geodesic incompleteness to challenging the notion of singularities, we've journeyed to the very edge of our understanding of the universe. But our voyage is far from over. There's an infinite cosmos waiting to be explored, with endless secrets yet to be revealed. So what are your thoughts? Are you captivated by the enigma of singularities, or do you dare to question the very essence of space-time itself? We're eager to hear from you. Share your thoughts in the comments below and keep the conversation alive. And don't forget to hit that subscribe button to stay tuned for more thrilling adventures in space science. Together, let's continue to push the boundaries of human knowledge and embark on even grander expeditions into the cosmos. Thank you for joining us on this awe-inspiring journey, and may our exploration of the stars ignite a passion for discovery within us all. Until next time, keep your eyes on the skies.